Okay guys, I am hoping that you have already answered the warm-up question, but if not, you can follow along with me right now. I'm going to go ahead and put the same screen that you are looking at up on my screen from My Open Math. So this is the warm-up question for today. It says, James walks 12 meters east, turns to walk north 7 meters, and then heads west 12 meters before turning to walk 7 meters south. Draw James's motion on the grid. You literally just have to click and then drag the mouse over to the next spot and click. You don't have to try to draw a straight line. But if I want to go ahead and do this, I'm going to start at 0 because that's just easier, and you could technically start somewhere else. But 12 meters to the east, there's 12 right there. Okay, and then it says north 7, and I'm going to treat, and it says on there, assume all numbers on the grid are in meters, and north is toward the top of this page. So I'm going to go up all the way to 7, which is right here, and then west by 12, which means I'm going all the way back to that position, and then 7 meters south. And so that is what you should have drawn, or something that looks like that is what you should have drawn on the grid. Okay. So follow-up question, how far did he go?
38.
Okay, I have an answer of 38 meters from over here. Does anybody have a different answer? 0. For the record, it will count either of them correct. Okay, it will count either of them correct because it really depends on how you are looking at this question. Because how far did he go is a vague question. Okay, how far did he go could mean how far did he physically walk, in which case, yes, 38 meters, but how far did he go if he ended up where he started? You could just as easily say he didn't go anywhere at all because he's right back where he started. And that goes to the root of what we're going to talk about in our notes today. We are taking some notes today, and they are on distance and displacement and scalar and vector quantities. Okay, so if you want to go ahead and take out your notebook or binder. Actually, let me go back real quick. You do have a homework assignment tonight. It's very short. I think it only has 5 questions. So it's a little reading assignment. There's a few different links to read through, and then there's a video, so you'll be able to read or watch the video, but bare minimum that you're supposed to read one of them. In fact, I'll give you a minute to read it during class today on motion maps. And then homework from last week, I'm hoping everybody turned in 104 graphing and reasoning problem set, but if you forgot, it is still in the late window. And so you can log into My Open Math and you'll still be able to complete that assignment. But in the late window, it is going to automatically deduct 20% of the points that you earn. So it's taking off 20% due to that assignment being done late. That late window will close, I believe, tomorrow is what it is set to do, but I'll double check. If anybody was absent on Friday of last week, let me know, because in that case I need to extend your assignment due date so it doesn't take off the late credit. Otherwise it's going to take it off. So make sure you talk to me before you leave today. Okay. So again, the answer to your warm-up question really depends on how you interpreted that question. Are you giving the direction along roads with twists and turns, or are you looking at an actual straight line distance? Because again, this wasn't the shape we had, but this goes to kind of the concept of 2 different ways that we can talk about how far something goes. And one of those is called distance and the other is called displacement. So these are the 2 terms that you're probably going to want to write down definitions for. By the way, again, if you know that you take notes a little slower than everybody else and you don't want me to skip past what you're writing, you might want to look at these notes on your own screen. I'm currently on slide 67. Distance is the total length of the path traveled. It is analogous to the odometer reading in your car. If in the warm-up you told me 38 meters, you gave me a distance. Okay, because if you had actually driven that, your odometer would have said you drove this far, because it's the physical path that you took. Displacement, on the other hand, is change in position. It is the straight line path from the starting point to the ending point. It is how far you are from where you started. Again, in the warm-up, if you told me 0 meters, you gave me a displacement because you were at the same point where you started. There was no straight line path to draw from start to end point because your start and your end point were at the same position. Okay, but if you had taken a path more like the one on my screen that kind of had a couple bends and twists and turns, then you can see a picture of what distance versus displacement would look like in that example. If you want to draw something like that, you're welcome to. But again, this picture on the left-hand side is how you would measure distance. If you physically measured the length of this dotted line path, that would be your distance. The image on the right-hand side is how you would measure displacement. Literally, I just care about where I started, where I ended. Okay, and you would get a straight line between those 2 points. Even if it doesn't fall along the roads, that's okay. All right, so that is kind of the difference. And again, in your warm-up, because I didn't specify, and we hadn't talked about it yet, that's why I didn't specify, either of those answers was acceptable, because how far, we can tell you how far we travel with either of those two terms, okay, distance and displacement. Obviously, they have different meanings, and so there are certain circumstances where I need one instead of the other, and if I ask you for distance and you give me displacement, you're going to get it wrong. Now, I will say this. If your travel is in a straight line and you don't turn, they're the same. If all you do is walk in a straight line, your distance and your displacement are the same. The only reason they're different is if you start turning and going other directions. Turn and go backwards, or turn to the left, or turn to the right. Okay? All right. When we discuss how far we travel, which again is what the warm-up question was asking, either distance or displacement, we need to define this with respect to a frame of reference. In the warm-up, it didn't tell you to start at the origin on that grid, but that was the logical place to start, would be at position 0, because that makes everything easier to count. Okay, but that was defining, when I chose to do that, I defined a frame of reference. Okay, and so frame of reference is going to be your perspective that is used to determine if and how an object is moving. So you'll choose some starting point, and typically it's easiest to call that point 0. Okay, we're going to start at position of 0, and then we'll measure everything from there. Although it doesn't have to be. You could pick something arbitrary and say, I'm going to start at 15. But again, that makes all your numbers harder, so typically we choose 0 because it's easier. If somebody asks, how far away do you live, the implied frame of reference is the school. So if I ask, how far away do you live right now, you would be telling me how far you live from here. It's implied that I am asking the distance away or displacement away that your house is from this building. Okay, and that defines your frame of reference, your perspective with which you're describing your motion. Distance is a scalar quantity. This is another vocab term, scalar. Okay, it's a scalar quantity. This is because the direction of motion, forward or backward or north, south, east, west, whatever, doesn't matter when you're finding the total distance. I didn't care that I went north and then south, or sorry, I went east and then north and then west and then south. I didn't care which way I went, I just added it all together. And so if you're not taking into account the direction of your motion, that's going to be distance. That's going to be a scalar quantity. Okay, it conveys only the magnitude, how much. Okay, magnitude, I guess, is another vocab word. That just means the number amount. I don't care which way. I don't care if it's positive or negative. I don't care if it's up, down, left, right, north, south, east, west. I don't care which way it is. I'm going to add it all together the same way that your car does. Your car doesn't care that you're driving backwards whenever you go home. You drive forward to school. You drive the opposite direction going home. It doesn't subtract it. It treats it like a scalar quantity. It just adds on there. It'd be kind of cool if you drove the opposite direction and it took miles off your odometer, but it doesn't work like that. Okay, so example, you could say my house is 8.2 kilometers away from the school. If you live in the Fairfield area, that's probably pretty close to accurate. But that would be a distance, because that would be along the roadways. Displacement is said to be a vector quantity. Again, that's a second term that you're going to want to write down here. There's two types of measurements. We're going to talk about scalar and vector. Okay, a vector quantity, we call it a vector because the direction of the motion matters when you find your total displacement. If I walk forward or if I drive forward and then I turn around and go the opposite direction, then my distance from where I started, or rather my displacement from where I started, is going to be affected by the fact that I went in the opposite direction. The direction matters with vector quantities. Okay, so displacement is an example of a vector quantity. A vector quantity is one that conveys both magnitude and direction. So when we talk about a vector, you're going to hear something like 8.2 kilometers northwest. It's going to have a direction associated with it. Sometimes when we indicate directions in this class, rather than using cardinal directions, north, south, east, west, you might see just a sign, a positive or a negative sign, because a lot of times when we work with especially one-dimensional motion, we define a certain direction as positive and another as negative. So you'll see positive or negative used as direction. You'll see cardinal directions, north, south, east, west. You'll see up, down, left, right. Okay, there are different ways that we can talk about the direction that we're going. So if you didn't write down those definitions, there they are. Again, vectors are quantities fully described by both a magnitude and a direction. Example would be saying that you have a displacement of negative 12. In this case, the negative sign means backwards. Scalar quantities are fully described by a magnitude or numerical value alone. There's no direction associated with it, so I could say a distance is 12 meters, and in that case, I don't know if that's forward, backward, or maybe it was 6 meters forward and 6 meters backwards. I don't know. It could be both. Okay, but it doesn't matter. We're just giving the scalar quantity there, just the number. I put this clip because if you're having a hard time remembering the difference between the two, then maybe Despicable Me can help you. Let's see if it will play.
Hey. I'm applying for a new film loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah! Check out my new weapon. Piranha gun! Oh yes! Fuck.
You don't necessarily need to see the piranha gun part, but if you can remember that, if you're having a hard time, remember Vector from Despicable Me. He is committing crimes with both direction and magnitude, so again, that goes back to the definition there. Okay, so we're talking about one-dimensional motion right now. Okay, one-dimensional motion is motion that occurs along a straight line in one dimension. Okay, so we're going to be going forward or backwards, okay, but not turning left or right. Everything's going to be in a single linear direction. So again, one-dimensional motion. Once we start adding in other directions, the warm-up did add in other directions, but that one was easy enough to do. But once we start adding in other directions, then you start having things where you have a diagonal, and we do that, but just not yet. So we often represent one-dimensional motion using a number line. A number line allows us to show forward motion or backward motion, but again, it's not going to take into account left or right because, again, we're just looking now at one-dimensional motion. Okay, so we'll usually represent it along a number line. We can represent motion with an arrow. So for example, and y'all can write any of these examples down if you want, but again, this hopefully is pretty basic and you're like, I don't really need this, but again, if you need it, write it down. We can represent motion with an arrow. So for example, if I say, you move 2 meters forward, you can represent that with an arrow that goes from 0 to 2 meters. Again, we typically choose our starting point as 0. You don't have to. I could have just as easily put this arrow back here and done 2 meters forward from -4 to -2. That still would be 2 meters forward. But again, oftentimes we will choose to start and define our frame of reference as the origin or the 0 point on our number line or on our grid. Okay, suppose you start at 0, walk 2,000 centimeters forward, and then 2,000 centimeters backward. Okay, if you want to do this on your paper, you can. It says make a number line and draw the motion. How far have you traveled? Okay, so again, how far have you traveled if you go 2,000 centimeters forward and then 2,000 centimeters backward? So it sounds like the warm-up question. Depends. Okay, it really does. Because how far is not specific enough of a question. Again, you're back where you started, so you could say you haven't traveled anywhere at all, or you could just as easily say that you have traveled 4,000 centimeters. Again, I would need to specify what is your distance if you do this, or what is your displacement if you do this. And again, when you read the questions that I give you in class, it's going to specify one or the other, so you need to make sure you know the difference between the two so that you can give me the answer that I am asking for. Okay, question for you guys to think about. Why is my picture not showing up? There it is. Okay, do you think it's possible for displacement to be greater than distance? Okay, take a moment. You can turn and talk to your neighbor if you need to. You have 19 seconds. Do you think it's possible for displacement to be greater than distance? See if your table can come up with a consensus. That is loud. Let's turn the volume down. All right, let's see. Cody, what do you think? Do you think displacement can be greater than distance? No, he says. Okay, and if you look at a diagram like this, you could see why that would be the case. If displacement is how far you are from where you started, it's always the shortest distance between 2 points, right? A straight line is the shortest distance between 2 points. It would be impossible for displacement to be greater than distance. Now, they could be the same. Again, if you just go in a straight line, they could be equal to each other. Okay, but it is impossible, and if you want to write this down, you're going to see this question on your test. Okay, it is impossible for displacement to be greater than distance, because displacement is the distance between where you started and where you ended in a straight line, and a straight line is the shortest distance between 2 points. They can be equal. If your motion is linear and in a straight line in one direction, they will be equal. Okay, but it cannot be greater. Your distance will always be greater or equal to your displacement. Does that make sense? You can even draw this picture if it helps to illustrate it for you. It's up to you. This is a very small mountains if this is only 200 meters. I don't know who put the numbers on here. Maybe this is like a toy motorcycle. I don't know. All right. Examine the diagram below. During which portion of the frog's motion did he travel the greatest distance? How do you know? Compare the vectors. Okay, so I have two vectors there, A and B. Which one represents the greater distance, A or B? A. Again, not a tricky question. I'm telling you guys this is an easy concept. Okay, A. And again, I know that because, well, one, the arrow is longer. You can look at the size of the vector, which is an arrow. Again, if you need to write that down, you can whenever you represent them. An arrow is a vector. Okay, or you can just look at the number line itself. A goes from 0 to 5. That's a distance of 5 meters. B, on the other hand, goes from 5 to 9. That's a distance of 4 meters. So you can use either the number line or just the length, the relative lengths of the arrows themselves. All right, if a frog jumps 5 inches and then 4 more, this motion is shown by the vectors below. Vectors can be added graphically by placing them head to tail as shown. And so if you wanted to add them, you would come up with something called a resultant. The resultant represents displacement. Again, if you need to make a note of that, you can. The resultant represents displacement in this example. You can also add other types of vectors, in which case it'd be different than this. But in this example, your resultant is displacement, and it looks like this. You just draw it from where you started to where you ended, because that's what displacement is how far you are from where you started. So your resultant would be the pink one at the bottom. Really easy to draw. So if I ask you to draw a resultant, that's all you're doing is drawing it from the starting point to the end point. And if they're all in one direction, it's super easy. But sometimes you change directions. Again, we're still just looking along a line, but sometimes you are going to go backwards. And I think I have an example of that in a minute. But the resultant vector shows the displacement at the end of the motion. It is drawn from the start, or the tail. Again, arrows have a head and a tail. The back end of it's called the tail. The pointy end is the head. Okay, but it's drawn from the tail of the first vector to the head of the last. So from start to end. Okay, and so that's my resultant in that example. All right, what about this one? Suppose you travel 5 meters to the west and then 2 meters to the east. Sketch motion with vectors. So again, on your paper, if you want to do this as an example, sketch this motion with vectors and then answer the two questions. What is your distance? What is your displacement? I'll give you a moment to add this to your notes. You have 21 seconds to write or discuss with your group, because you've got questions there as well, so make sure you know the answers. I know it's first period, but if you're not sure, definitely ask your neighbor in case I call on you. Timers are going to wake y'all up if you fall asleep. That's pretty loud. All right, so again, sketching that. Okay, 5 meters to the west, I added a compass rose up there. Hopefully you know north, south, east, west. You know your cardinal directions. But if I wanted to draw 5 meters to the west, it looks something like this. And then 2 meters to the east, I'd be at the end of that first arrow going back east. Okay, so that would be what you would look like if you went west and then back east. So what is the distance here? Let's see. Taylor. Yeah, 7 meters. You're just adding them together. Again, like the odometer would on your card. Doesn't matter which way you go. You're just adding them up. Okay, what would my displacement be though, Sean?
3 meters.
3 meters. Okay, and again, you can represent your displacement with that resultant, and that will show you the displacement, but that would be your resultant. And if you had a number line there, you could also see it that way, that arrow would represent 3 meters of length, okay, or 3 meters of displacement. But again, the fact that you go to the west and then to the east matters. Your displacement, though, needs to not just be the number, not just 3 meters, but 3 meters in which direction. And so up there you see I wrote 3 meters west. Okay, it needs to have a direction as well. That's the part that a lot of students forget whenever they are writing out the displacement. You might even do the math right, but you have to also include the direction. Any questions about that? Okay. You can also represent one-dimensional motion with a motion map, okay, if we consider the time of the motion. I have a reading for you in Schoology, and actually it's in your homework assignment for today, which is assignment 105, motion maps. So if you want to head to Schoology real quick, it's a single page of reading. I'll show you exactly what it looks like actually. But if you open up this assignment, or you can go straight to that little link down there, that tiny URL link, but I'm going to show you what it looks like first. So here is the assignment 105 in Schoology. And if you click on this, it opens up this. You'll put in your name and ID and all of that. Click next. And then here's what I'm talking about. This is the reading selection you're doing. There are other readings in a video that might help in addition, but at the bare minimum, you need to read this. And it's very short. It is literally a single page, if it decides to load. There are pictures on it that haven't loaded yet. But it's just there they go. It's a single page. That's it. So that is what you should be reading right now. Again, you can get to that through Schoology, or if you prefer, you can just use that tiny URL link at the bottom. But I'm going to give you guys a couple minutes to read that, and then we're going to come back and discuss motion maps. You have 4 minutes to read that single page, to get to it and to read it. Okay. Hopefully you read that. If not, no big deal. You have it to read as I'm continuing to go over this, or you can finish reading it later on after we're done, since it is part of your homework anyway. But again, we are going to talk about motion maps, so I wanted you to kind of look at them first. This is what a motion map looks like. It looks just like what we were looking at before, except in addition to this now giving us distances that are being traveled, each arrow represents an increment of time, and we typically use seconds unless it tells you otherwise. So in this case, this first arrow represents 1 second of motion, and the second one represents a second of motion. And so I have a data table over here as well for the same thing. It said 5 meters to the east and then to the west and then 2 to the east. So I have my 5 meters to the west and then 2 to the east. But it happens in 2 seconds now. That's it. That's the only difference, is that we're associating time. And it didn't necessarily have to happen in 2 seconds. That's just the data that I gave you. Okay, so when you read a motion map, it starts from the lowest arrow. And the reason that they're stacked, you're not actually going up in the motion. It's still just back and forth. It's just if you drew them all on top of each other, you wouldn't be able to see them. Okay, and so this just represents, we're still going in a single line, but this represents going 5 meters to the west and then 2 meters to the east. And so you end up at this position. You started there. You are still 3 meters west of where you started. But again, that's what a motion map would look like. It's the same thing that we drew before. It just has a number line with it, and now we are incorporating time. Yes?
Does the dot, what's with the dot? Does the dot have to be there?
Yeah, I'm going to show you this right now. Okay. So this says draw a motion map for the following scenario. And if you want to write this one down, you can. But it says starting at his house, and I've defined it for you. I'm telling you that the starting position, we're going to use 0. John runs 10 meters east to Kim's house at a constant speed in 2 seconds. When he gets there, he stops for 3 seconds to drop off a package, and then he walks 3 meters west, back 3 meters west to Ryan's house for 2 seconds. Okay, I don't know why he's going and stopping at people's houses for 2 seconds, but whatever. And so we're going to start at 0, and I have a data table here as well that will help. But from 0 to 1 seconds, he's going from 0 to 5 meters. And so the first arrow that I draw will look like this, from 0 to 5 meters, and then from 5 to 10 meters. That's the first section. Now, we don't typically label the times on the arrows. We just know that first one is the first second, the second one is the second. They're not typically labeled. I'm just showing you how to do it. Okay, after that, he stops, okay, for 3 seconds. And so if I want to show that he's not moving, okay, but time is passing, we use a dot, okay? And so for this portion right here, you would see dots. And again, so that we know so we can count how many dots there are, they are going to be drawn upward. He's not moving upward, it's just that's how we're going to count them, okay? Because if we put them all on top of each other, you can't see how many there are. Okay, so that represents these 3 seconds that he stopped, 1, 2, and 3 seconds. Now we're to 5 seconds because this one was 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5. Okay, and then he starts to go west. Okay, and he goes to 8.5 meters the first second there, and then to 7. Okay, and so I end at 7 meters just like it shows in my data table. Okay, and that is what your motion map would look like. It wouldn't have any of the numbers on it, it would just look like that. Okay, so that shows the exact same motion that was described in the paragraph and that is shown in this data table. So a motion map is just a way to visually represent one-dimensional motion. You can't show turns on it because it's literally along a number line. There's no left or right, it's just forward or backward or stopped. Okay, so we can have some questions here that we're going to analyze this motion map. Okay, so the first question says, when is John moving fastest? And I want you guys to talk about these as a table because I'm going to run a timer again, give you a second to discuss, and then we're going to call on some people. But when is he moving fastest? What is John's change in position after his first 2 seconds of motion? What is John doing from 3 seconds to 5 seconds? What distance did he travel? And what is his displacement at the end of his motion? So I would like you to see if you can discuss these. A lot of this was answered in the reading as well. Okay, and I'm going to set a timer for 40 seconds because that's a few questions to answer. So talk with your group, and I'm going to call on some people when the timer goes off. Definitely talk to them if you're not sure. Okay, let's see. Connor, when is John moving fastest? What do you think?
Between 0 and 2 seconds.
Yeah, the first 2 seconds he's moving fastest. In the reading it said that the longer arrows represented faster motion. That's because you're going a greater distance in the same amount of time. If you go farther and it only takes you a second, for that than it does for another one, it's going to be faster. Thank you, Connor. Good job. Okay, what is John's change in position after his first 2 seconds of motion? What do you think, Caitlin? Sorry? 10 meters. That, when I say change in position, that is displacement. So I'm asking you how far he is from where he started. Since he was going in a straight line, yeah, he's 10 meters away. You can use the table or you can use the motion map for that. Thank you, Caitlin. What about the next one? What is John doing from 3 seconds to 5 seconds? What do you think, Braylon? Standing still. Yeah, he's not moving. Those are those dots. Or again, you can look at the table. His position is staying the same. Even though time is passing, that means he's not moving. Number 4, what distance did he travel? Chase. Yep, so he goes 10 meters forward and then 3 meters backward, but I don't care about the backward or forward. I'm just going to add it together. 10 plus 3 is 13 meters. Thank you, sir. Okay, and then what is his displacement at the end of his motion, Sumeda? So he's 2 meters from where he started. How far is he from where he started? Because that's our definition of displacement. There you go, 7. Again, you can see it in this diagram pretty easily. He started at 0, he ends at 7, so he is 7 meters away. Or you can see it here. He started at 0, he ended at 7. He is 7 meters away. Now, we also need a direction, so we would say 7 meters, and I think we used east and west here, so we'd say 7 meters to the east. Or you could say positive 7 meters, or 7 meters forward from where he started, or to the right. But you need to indicate a direction of some kind. So not just 7 meters, but 7 meters with a direction. All right. Thank you, Samita. Okay, so that's a motion map. Okay, now again, right now we're just looking at one-dimensional motion. So just forward and backward, or it could just be up and down. Okay, we don't have to do left and right. We could go north, south, up and down, whatever. But if you do have motion in more than one direction, you will have to separate your vertical motion from your horizontal motion. You'll have to add your vertical components together and your horizontal components together separately. Okay, we're not really going to mess with this just yet, but I did want to just mention it. Okay, as a convention, we treat up and north as being positive. If we're looking at vertical motion, anything that goes up we typically think of as positive, or we call north positive. We treat down or south as negative. Horizontally, we treat right or to the east as positive, and left or to the west as negative. And the reason we do this is because of the way that the coordinate grid is set up in your math class. Okay, if you think of the coordinate grid in math, you know that on that grid, anytime you go up, that's positive numbers, down's negative. Same thing with left and right. Anytime you go to the right, those are your positive numbers, to the left are your negatives. So we do the same thing in here by convention. Technically, you don't have to use that convention, but that is typically what I will use. Okay, so if I asked you for displacements here, this one you'd say positive 4 meters. This one you'd say negative 2 meters from where you started. So if you went up 5 and then down 1, you'd be 4 meters from where you started in a positive direction, or up. Here you would be, if you went 4 meters to the left and then 2 meters to the right, you'd be 2 meters left of where you started, or you could write that as negative 2. The negative sign shows direction in physics class. All right, so here are a few more to look at. I'm asking you for distance and displacement. Distance is the d. Change in position, delta x, is displacement. Okay, so if you want to write down the variables as well, you can. But if you'll take a minute, I'd like you to look at each of these and see if you can figure out your distance and displacement in each example. We'll go over a couple of them, but turn and talk to your neighbor. You have 36 seconds to discuss.
Sticking spaghetti sticks with gum below the table.
That's lovely. Good to know. Okay, so let's look at, I'm actually going to skip A because that one's pretty easy. Let's go to B. Distance traveled by the object represented by that blue arrow for B. What do we think the distance is for that one, Diego?
3.
Yeah, if you're going from 12 to, what, 7?
8. Yeah, 7.
That's why out of the dashed lines. If you go from 12 to 7, what would you call your distance? 5. All right, so that'd be 5 meters. What about the displacement from those 2 points, Ava? Perfect. You put a direction on it. Okay, 5 meters west, or you could put -5. Okay, but you need to add a direction to it. A would be similar, except you'd have your direction, then A would be east or positive. You'd have to actually write the positive sign. What about letter C? What do we think our distance is in letter C, colon? Sorry?
For C.
For C.
12.
Yeah, so you're going forward from 2 to 10, so that's 8 forward. And then you're going backwards 2, that's 10. And then forward 2, that's 2 more, so that's 12. Yes, that is absolutely correct. 12 meters would be your distance for letter C. What about the displacement for letter C, Stuart?
8.
Yeah, just how far are you from where you started? East. Yep, 8. And then a direction east. Perfect. All right, so again, that is how you're going to do these. Again, hopefully you figured out A and D as well, but I just wanted to look at a couple of them. Okay, for the rest of the class period, you have a homework assignment, 105 Motion Maps homework in Schoology. Most of you already opened it because that is where the reading was. Again, there are a couple other links in there on distance and displacement and scalars and vectors on a website called Physics Classroom, which is a good resource for you if you're ever looking for some extra stuff to help you if you're struggling with anything in here. It's a good website. But you should definitely read those before you answer the questions. There's also an optional video clip that you can look at. And then I need to actually post the unit summary. It's not there yet. But there is a section in the unit summary which is going to be basically a bunch of questions that cover the entire unit. We use the unit summary, and this was in your syllabus as well, as a daily grade redo. So if you forget to do your homework, maybe you forgot on Friday to turn in 104, or if you have just a bad grade on a quiz or whatever, the unit summary is the daily grade redo. So you would do that, and I would be able to replace your lowest failing daily grade up to a 70 because it's a redo. In the past, we have also typically counted the unit summary as bonus points for the test. I'm going to check and see if we're still doing that, but it's not posted in Schoology yet. So you actually can't do that yet, but you can do this. 105 Motion Maps homework, that is what I'll let you work on for the remainder of the class period, which is only about 6 minutes, but it's, again, only 5 questions. So if you already have it opened up, you should be able to get it done. If you don't finish it in here, you will be finishing that for homework. Do not forget to turn it in.